So after annular slices and cylindrical shells, we're going to do volumes by cross-section. Okay, here's why, right? Let me give you a shape. I'll try and draw it as accurately as I can. And I'd love you to draw it as well because we're going to do some manipulation with this in a second. Here's my impression of a square pyramid, okay? Here's the base. Now think about this. This is quite emphatically not a solid of revolution. So you cannot do it by annular slices because there's no way you can cut it up where you'll get these shapes out. And you can't do it by cylindrical shells either. But I can cut this thing up in such a way, right, so that I get a whole bunch of infinitely thin slices, right, that all share very common characteristics because it's a square pyramid. So which way would I cut this up to get shapes that are similar to each other? Now I think if we cut it horizontally, right, at least according to the way I've drawn it, if I cut it horizontally, then being that I've told you it's a square pyramid, right, each one of the pieces, right, I can't call it a slice, an annular slice, I can't call it a shell because they won't be. What will the pieces be? They will all be squares. Every single one, right? So we could do a whole bunch of squares and the smallest one would be up here. A square of width 0, I guess. Okay. So let's try this. In order to do it, to actually calculate this, let's say it has a perpendicular height of h, height h, okay? And because it's a square pyramid, I need one other measurement. What do I need? The base, I need its side length, don't I? So let's just, for the sake of illustration, let's just call that A units, okay? I suppose I ought to say that we'll make it a right pyramid, so it's going to go straight up rather than off at an angle. But in some senses that wouldn't matter. But let's just keep with this, okay? Now, how am I going to do this? I want something like this. I want to get toward this, okay? So I need to decide which way I'm going to slice this. We said horizontally, right? Now there's no coordinate system here. So let's introduce one where we can take different values, which will give us different slices, okay? So right now, I'm going to look at this side on, okay? Because this 3D is confusing me a little bit, right? Here's what I'm going to do. Okay. Now, this is a little unusual, but I'm going to look at it from the angle of not like directly from the side or directly from the front. I'm actually going to look from the diagonal, okay? Why would I do that? I want you to have a think about why I would do that, okay? If I looked at it directly side on, okay, when I take those slices, what are my measurements going to be? See, the problem is they're not going to go through my axis, right? In a similar way that I have an axis of rotation here, right? I don't have an axis of rotation here, but I do have something that everything turns around, namely the from the apex down to the base, okay? And I want to have that on my diagram, okay? It's harder to actually do calculations from that if I'm looking side on, okay? So therefore, I now have this distance here, which is h, right? That's the perpendicular height. But if I'm looking at a diagonal, this is not A, right? This width across here. This is this diagonal here, right? So if it's not A, what is it? It's a square, right? Square base, okay? If you look at it from the top, okay, you've got A here and A here. This is a 45, 45, 90 triangle, or alternatively, if you want to go Pythagoras, right, you're going to get the square root of 2A. Is that all right? Cool. So now I have a measurement down here. Okay, now, I want to cut this into pieces, right? And I also need an axis. So I'm going to say, let's put a piece, an arbitrary piece in here. Okay, so this is my cross-section. This is what you told me to do, to cut across horizontally, okay? And if I were to take this out and flip it over, you'd get a square, no problem, okay? So there's my cross-section. I need an axis here, so I'm going to call this the x-axis, right? And this is what's going to vary, right? This is how I'm going to be slicing this guy up, okay? So if this is x, and this is h, and this is the square root of 2a, okay? Don't forget, this is constant, this is variable, right? So number one, what have I built so far? I can say, what's the width of the cross-section going to be? It's going to be delta x, isn't it? Because that's how I'm cutting this thing up, right? So I want all of those to be very small, okay? Now I'm going to add up a whole bunch of things, okay? What is the variable that's going to change? Again, it's going to be x. That piece there, 1, 2, 1, 2, it remains consistent, right? So I'm trying different values of x, okay? Now, we're used to getting boundaries provided to us like this, okay? The boundaries of the volume I'm after are right here on the diagram, but because there's no coordinate system, it's hard to see them, right? What will be the smallest value of x that I can have? The smallest value of x I see will be 0. It'll happen right there, okay? You see up there, it'll be 0, okay? What's the largest value of x I could take? It'll be h. That's as far as I go, right? So therefore, this volume I'm going to get is from 0 to h, okay? Now, keep going. I need some extra pieces in here. I already know what this one is going to be, the width of each cross-section, okay? That's going to be delta x, okay? But now the piece that I'm missing, and this is the part which takes some work, okay, is in here, right? What belongs there? If I've already taken into account the how thick each cross-section is, right? All that's required here is the area of the cross-section. In this case, it was an annular slice. In this case, it ended up being a rectangle when you unfold it. In this case, it will be a square. You identified this at the beginning, right? Namely, it'll be, for instance, it'd be a square like this. There you go. There's one of my cross-sections. Okay, maybe I'll make this blue so you can see it's referring to the same thing. Okay? So, I want to know the area of the cross-section. It's just a square, right? So what do I need to know to work out its area? I need to know its side length, don't I? I need to know what this is. How do I do that? I've got similar triangles here, don't I? In fact, I have to have some kind of similar figures in order for the cross-section to have some kind of consistency. Because otherwise, I've got nothing that I can put in here that will be true for all of the different cross-sections, okay? Right, so how do I work it? Similar triangles. It looks to me like this thing here is the diagonal of the of this square, right? It's this distance over here. So being that it's a diagonal, I'm just going to call it D. D for diagonal, okay? So what can I say about this diagonal? Based on similar triangles, I think D, the little diagonal, on the big diagonal down here, right, is going to be equal to small triangle, big triangle, small triangle, big triangle. You okay with that? That's from similar triangles. Thankfully for you, you have gotten to a level of mathematics where you no longer need to prove that triangles are similar. You can just say that lovely phrase that 4 unit students love, which is by inspection. There you go. Because I looked at it and said so. Now, all right, I have this, right? So what I actually want is D, isn't it? Right? That's going to give me, that's what I can put into here to get the area of the square, right? So I'm just going to rearrange that. I guess I'll say AX times root 2 on H. It looks awkward, doesn't it? But it's okay. A is a constant. Base. H is a constant. Height. X, it has to be variable because I'm going to integrate with respect to that in a couple of minutes, okay? Okay, how do I go from the length of a diagonal to the area of a square? How do I do it? It's a diagonal, don't forget, right? It's actually not a side length, okay? So I can't just square it. If I told you, here's a triangle, a square, and its diagonal length, for instance, was something like, oh, I don't know, call it 10. Now clearly you can work out the area of this square. How would you do it? You need to know side length, don't you? You need to know side length. So you could do these by Pythagoras. That would work, wouldn't it? But there's a simpler way. There's a simpler way, okay? Because this is 10, isn't it? This is 10. What's the length of the other diagonal? It's a square, so it's 10. Can you see why? Are you familiar enough with your quadrilaterals to see that the area of this guy is half times the product of the diagonals? Can you see it? If you can't see it, maybe let me draw in some lines. Okay, does that make it any clearer?
Yes.
For those of you who didn't say yes, does that make it any clearer?
Yes.
Can you see what I've done? I have made a new red, larger quadrilateral, right? Because I have these diagonals being perpendicular, right? These sides are also perpendicular. But what are the side lengths of this new shape that I've drawn, the red one? It's 10 by 10, right? But this new one is exactly twice the size of the shape I started with, okay? In fact, you don't only do this with squares, you do it with anything that has perpendicular diagonals, right? Do you remember learning the area of a kite? Do you remember the area of a kite? The area of a kite is half xy, where xy are the diagonals. Do you remember learning the area of a rhombus? The area of a rhombus is half xy. It's half the product of the diagonals because the diagonals are perpendicular in both cases. Anyway, now I know I can deal with this square, okay? So if this is the diagonal, right, then the area of the square that I'm going to put into here will be, I actually need a bit more space, don't I? It's going to be half times d squared times the thickness of the cross section. Is that okay? You following with me so far? Is that all right? I'm going to substitute in what d is because I know what d is, okay? Limit delta x approaching 0 from 0 to h of, okay, half times ax root 2 on h squared delta x. Okay? What's going to happen here? 2's will cancel, right? 2's will cancel. A half there. There will be a 2 there, so they'll disappear. Okay. What else is going to happen here? You're going to get an a squared and an x squared and an h squared, right? Tell me, which of those are constants again? A and h. A and h. So just like before, wherever I see constants, I just whack them out the front because they are inconsequential to the actual integral, right? Okay, so I've used this result, so I'm going to rub it off so my integral can just keep going. Okay, so here we go. Watch what happens. I'm taking these constants out. You told me the a squared and the h squared were both constants. So out they go. Integral from 0 to h. Okay. The half and the square root of 2 squared, they've disappeared already. So what's left in here? Just x squared with respect to x. Is that all right? Okay, so I know how to integrate this because I'm super good at integration. X cubed on, 3. From 0 to h? Yeah, is that okay? So what am I getting? A squared, h cubed on 3 minus 0. H's are going to cancel. So you end up with a third, a squared, h. Or in other words, what you already knew to be the volume of a pyramid, namely a third times the area of the base times its height. Cool. So, let's just review. What did we do? We used this thing, this guy up here. Remember I said the hallmark of powerful mathematics is its ability to smoothly transition from one kind of problem to another. Okay? This line here is so the same and yet so different from the previous volumes. But it works, right? So you see what we were doing. I had to do some work to get from here to here. How did I do that? What mechanism did I use? I used similarity, didn't I? I had to draw these guys, right? Diagrams are your friend. Sorry, I take that back. Good diagrams are your friend. Okay, bad diagrams, not your friends. Once you did that, and you've got that in terms of the right variable, okay, it's mechanical from there. Right? So all the work is up here and in here. Okay?